In this project, I attempt to solve an elliptic PDE by transforming it into linear system equations and optimizing the quadratic function using the conjugate gradient method, which improves a little in algorithm and is more efficient than the gradient descent method that is discussed in class. The conjugate gradient descent method is an improved version of the gradient descent method. It is widely used to find the nearest local minimum of a function of n variables, which presupposes that the gradient of the function can be computed. It uses conjugate directions instead of the local gradient for going downhill, and if the vicinity of the minimum has the shape of a long, narrow valley, the minimum is reached in far fewer steps than would be the case using the method of steepest descent. In this and during the class, we have viewed the following examples that are used with gradient descent, like Newton interior point, search direction least square normal equations, and the regularized least square equations, etc. However, we note that steepest descent often finds itself taking steps in the same direction as earlier steps. So it would be better if every time we took a step, I got it right the first time. So here's the idea. Let's pick a set of orthogonal search directions, and in each search direction, we will take exactly one step, and that step will be just the right length to line up. And so to do this, we will follow the following algorithm. We will first create iterates, then create residuals, find search directions, and based on the search directions, we will use iterative method to update our variables. And so here, let's take a look at how they can apply to elliptical PDE. We now aim to solve this equation, and so by finite element method, we can write it separately as a linear system. So by setting up the initialization, like I set h equals to 0.1, so that n equals to 20, and the error tolerance is 1 to 10 to the minus 5. And here error is the norm of residual over norm b. And I use the error to track how fast the residual will decrease to reach this tolerance. And I plot the tolerance out for conjugate gradient method and the steepest gradient. And from these two plots, the x-axis are both iteration numbers, and the y-axis is the norm of residual. And we can see that in as the conjugate gradient method will converge faster, like it use only 4 to 6 steps to reach our error tolerance. However, it still takes an steepest gradient a lot. So I conclude that when solving large system, the conjugate gradient method is a better choice. And we can also improve this method by giving a preconditioner. Like we now have the Jacobi I preconditioner, SSOR preconditioner, etc. However, I will not discuss it further. So that's it. Thank you.